Hello again. Welcome back to our video lecture series. This video is about a partial differential equation known as the wave equation. Strings on musical instruments are placed under tension so that when they are struck, they produce predetermined pitches, or musical notes. The sounds we hear and the relationships between the notes that we perceive as melodies and harmonies are the result of mathematical relationships in the frequencies at which these strings vibrate. Notes that sound good together generally exist at frequencies in simple mathematical ratios from each other. When you hear musical harmony, your brain is taking information from your ear and calculating the ratios between received frequencies for free. As Wilhelm Leibniz, the co-creator of calculus, puts it, music is the hidden arithmetical exercise of a mind unconscious that it is calculating. In other words, music is what happens when your brain does math without you knowing it. While the harmonies of vibrating strings have fascinated philosophers and mathematicians since the ancient Greeks, it wasn't until around 2,000 years later, after Newton and Leibniz invented calculus, that vibrating strings could be mathematically modeled. This required, as you may have guessed, a differential equation. The equation which models a vibrating string was first derived and analyzed by the French Enlightenment figure Jean-Le-Rond d'Alembert in the year 1746. D'Alembert was a mathematician and a music theorist, amongst a litany of other things. In this lecture, we will use the tools we have learned to derive and analyze the equation of D'Alembert, known now as the wave equation, and obtain mathematical insight into the musical vibrations of strings. In order to neatly formulate the one-dimensional wave equation, it is necessary to make a number of simplifying assumptions. The string is homogeneous, meaning that it has a constant mass density. The string is perfectly elastic. Displacements in the string are small relative to the string's length. Displacements take place only perpendicular to the x-axis. These are called transverse waves. The slope of the curved string is also small. The tension in the string is uniform throughout, the tension is large compared to the force of gravity, and there are no other forces acting on the string. Consider a small element of mass along the string. It experiences the same tension, T, at either end. The components of this tension in the x direction are then given by sine theta, where theta is the angle that the slope of the displaced string makes with the x-axis. Under the assumption that this angle is small, the sine is approximately equal to the tangent of this angle. But the slope of the tangent line is the derivative of the displaced shape at this point. We therefore have this expression for the quantity of force along the differential mass element. Using Newton's second law, we can set this force equal to the mass times the acceleration of the string. This is given by the differential delta x, a mass density per unit length, and the second partial derivative of the displacement with respect to time. Rearranging, we have the differential difference in the first derivative with respect to x divided by a small differential distance. Taking the limit as delta x goes to 0 gives us the second partial derivative with respect to x. This yields the 1D wave equation. Just like with our derivation of the 1D heat equation, this derivation generalizes to problems with vibrations in higher spatial dimensions. The wave equation generally takes this form, where the Laplacian operator is the sum of second partial derivatives. This equation can then be used to model vibrating membranes or solids. In this video, however, we will focus on its 1D form, used to model a vibrating string. Here is the 1D wave equation given alongside a series of boundary and initial conditions. The boundary conditions state that the string is fixed at both ends, just like it would be on a guitar or a harp. There are also two initial conditions. One represents the initial displaced shape of the string, given by f of x. The second prescribes an initial velocity distribution, given by g of x. Again, the analysis proceeds by separation of variables. This yields three possible solutions for both the x component and the t component of our solution. Just like in the heat equation, the boundary conditions fix the trigonometric form in x, leaving only a sine term. For the t component, we select the trigonometric form as well, since it will help us fix the constant required to satisfy the initial conditions. This leaves us with a family of solutions for each natural number n, which can in general be combined into an infinite series solution with two free constant parameters per term. The arbitrary initial conditions can then be approximated using Fourier series. The coefficients an correspond to the initial position f of x. The coefficients bn correspond to the initial velocity g of x, and can be calculated by taking the first time derivative of our solution. Here are the general forms of the Fourier coefficients. We have therefore derived a general solution to our combined boundary and initial value problem. The coefficients an and bn will yield a series solution that converges to any given initial position and velocity distribution for a string with two fixed ends. The solution for a string's vibration is therefore a sum of an infinite number of wave terms, each with their own frequency. When you pluck the string of a musical instrument, the pitch you hear, along with the specific character or tone for that specific instrument, stem from the superposition of a large number of these individual frequencies. These individual waveforms are called the normal modes or standing waves of the string's oscillation. Each subsequent standing wave will have one more point where it does not vibrate, known as a node. By stopping vibration of a string at a node on a musical instrument like a guitar, you can damp out the lower standing frequencies. This will leave only the higher frequencies that share this mode vibrating, and you will hear what are known as overtones. Let's have a listen. This guitar is tuned so that its lowest string vibrates and sounds an E note. If I stop the string from vibrating at some of its nodes, you can hear the string's overtones. Let's hear that again through some sick effects pedals. Where were we? After that little aside, I think it's worth going through the calculations for a practical example. If a string is pulled taut to a height h at a point P along its length, its initial profile will be piecewise linear, like this. At the instant of its release, its velocity profile will be 0 at all points along its length. How will the motion of this string evolve in time? Since g of x equals 0, we only have to worry about calculating the Fourier coefficients an. Since the function to be approximated is piecewise linear, the integral required here can be broken up into two. The first from 0 to p, and the second from p to L. We have calculated integrals like this in the past. It can be done by integrating by parts once. I will spare you the details, but if you feel like you need some integration practice, try them out yourself. Here are the results for the two required integrals. Adding the results of the two integrals together gives the result for the coefficients an, and this provides us with our series solution to the problem of the plucked string. We can plot the string's shape at small time intervals and have MATLAB piece them together into a movie. Here's a video of the vibration of the plucked string. I have set the problem parameters a, h, and l equal to 1. The location P, where the string is plucked, is at 1/3 of its length. The plots you see are from the first 1,000 terms of the series solution. Thanks for watching this video about the wave equation. Stay tuned for more content.